I'm Robin, and for today we're gonna answer a sample shortest path problem, particularly the concept of the Chinese postman problem. So, due to the rising crime rate in the community, authorities instructed local enforcements to make rounds around town every day. Suppose the police station is based on point A, find a round that covers all points from A that will yield the least or smallest possible route. So we have our given figure here with um, the police station basing at point A. So we would um, originate here. So we start off by identifying the odd nodes. Odd nodes. So what are odd nodes? So odd nodes mean that vertices with the odd number of paths. So this means that the vertices that has a number of paths which are odd are considered as odd nodes. So in our case, if we will look here, we have B, which has three paths. Let me highlight this. There we go. We have B. B has three paths. So we'll consider B as an odd node. Next one is we have letter C, which also has three paths. Next is we also have letter D, which also has three. Then lastly, we also have letter E, which has also three. So in our case, our odd nodes are B, C, D, and E. So after identifying our odd nodes, we proceed with the pairing. So consider each nodes. So um, our process in pairing will refer to the odd nodes we've identified. So if this is our odd nodes and we proceed to pairing, we can have um, a random assignment for um, two vertices. So if we have, for example, BC, then probably D is gonna be paired with E. Next, if we have BD, then probably C is gonna be paired up with E. Next is if we have BE, then D is gonna probably be paired up with C. So we have DC. So there we go. So after assigning or setting up the pairing, next is we get the total lengths for each pair we've assigned. So let's put it in a separate one. B, C, B, D. Sorry, this is D. Then BE. So for BC, we have 5. As we can see here in our figure, from B to C, we have 5. BD is 7. Then B to E is let's see first. So if we consider the routes from B to E, we have plenty of options. So looking here, if we go from let's say B to C to E, oh sorry, we'll have a total distance of 13. But however, if we what you call this, look for an alternative route, we can see that we'll have from B to C to F to E is a total of 12. So it is much shorter than the one we've come up with initially. So we'll consider 12 as the shorter distance or the shortest distance from B to E. Next, for the next set, DE, CE, and DC. For DE, we have 6. CE is 8. But wait, let's try to look again. If we go from C to E, we'll have 8. However, if we'll consider other options, it can also be C to F, then F to E, which has 7 as its total. So it's much more smaller than 8. So we'll consider 7 as the distance from C to E. Then lastly, we have DC. Again, we'll look for a minimal path. So from D to E to C, we'll have 14. So I guess we can still look for other options. From D to B to C is 12. 12 can be the value, but let's still check for others. So from D to A to B to C is also 12. So it's the same one. Next, if it's D to E and E to F and F to C, we'll have 13. So we can say that 12 is the shortest possible distance from D to C. So we'll write 12. So next, after getting each length of the pairs, we add both of the values. So after adding both, so let's add the respective values for each pair. So we have 5 plus 6, 7 plus 7, and 12 plus 12. 5 plus 6 is 11, 7 plus 7 is 14, and 12 plus 12 is 24. So after adding both pairs, we identify the smallest value here. So between 11, 14, 24, we can see that 11 is the smallest. So we'll be making use of this one, the row right here, because it has the smallest value. Next is we identify the total distance found in the figure by adding all of the values per vertices. So in order for us to do this, we just simply add what's all of the numbers displayed per path. So if we have 3 plus 4 plus 6 plus 3 plus 4 plus 5 plus 7 and plus 8, we'll have 4 plus 3 is 7, 7 plus 6 is 13, 13 plus 3 is 16, 16 plus 4 is 20, 20 plus 5 is 25, 25 plus 7 is 32, 32 plus 8 is 40. Our total distance is 40. After getting this, we add this to the smallest value we got from adding the pairs. So it is 11. So we'll write here, add them both. 11 plus 40 is equals to 51. So we now have our shortest or least possible route for our problem. So however, we only identified the distance, so we'll still have to find the path. The path that should be taken by the local enforcements. So in order for us to do this, we should look for the path which will represent 51, the number we've got. Note that BC and DE can be passed through twice. So we can make use of BC and DE as routes which can be passed through more than once. So we can do that by simply adding a curve like right here. So BC and DE. So we can have added alternative routes. So let's start. So note that in our with our objective we have to visit all the vertices present in the figure. So after being able to visit them, we should return back to our original point, which is CTA. So we'll start off in CTA and also end up in CTA. So let's start. From CTA, we can go to CTB or point B. From B, we can go to C. From C, we can go to F. From F, we can go to E. From E, we can go to um wait, let's try and check that again. So from C to F, F to E, then E to C, sorry. E to C, then C to B, B to D. Note that if we return to oh no. No. Yeah, it's still correct because we've already um went through with all the points. So we can say that from D we can go again from E, then E to D, then A. So we forgot that we should um visit all the possible routes and cities. So yeah, there we go. We have our path. So again, we went from A, then B, C, F, E, then C again, B, D, E again, then D, then finally A. So we can have our least or smallest possible route. So we can indicate that from the path A, we go to B, then C, F, E, C, B, D, E, D, then finally A. So this one is this particular paired paths are the least or smallest possible route that the local enforcements can take in making their rounds at the different points or cities. So that's all. Thank you.